One great. That's good. Wow. Well, I'm glad. Do you guys have any questions about things? Stuff you lost sleep over? Okay. Give you a chance. Last time we started linear motion, chapter 3. And we got some basis so that we make sure everybody understands terminology. With speed, let me write a few formulas down that we saw. So speed is related to distance and time. The faster you're going, the farther distance you'll travel, or the more quickly you will do it. How did velocity compare to speed? It has direction. So which one is a scalar? Speed is called a scalar. It's just magnitude only. What's velocity called? A vector. Vectors have direction. What do you think force would be? A scalar or a vector? A vector, because it has direction. So you know which way you're being pushed or pulled. Good. Acceleration was what? I heard it. Good. Velocity over time. Technically a change in velocity over time. So speed and velocity are how fast you're going, and acceleration is how quickly you're changing how fast you're going. Remember, this was in meters per second, and this one is in meters per second squared. So you're going to change your velocity, meters per second, every second. And then I gave you this equation. The initial velocity, this is your initial velocity. If you're already going at a certain speed, or if you're starting at rest, this would be 0. And you want to know how fast you'll be going sometime later, well, that's dependent on your acceleration. So if you're not accelerating, you stay at the same speed. If you are accelerating, let's say at 10 meters per second squared, then after 3 seconds, how fast are you going? If you started from rest. 30, because the first second you change by 10, the second another 10, and the third another 10. 10 plus 10 plus 10. So you'll end up going 30 meters per second. This works for everything. I wrote it last time where this was a g. Does that change things? Does that make it different? That's just a specific acceleration due to gravity. So this works vertically when something's falling at that acceleration. But it works in any direction also. And then where I left off, we were going to do this one. Yeah, I'll just write it. When you're dropping something, the distance it falls, that's how you'd find it. It's a 1/2 times the acceleration due to gravity times the time squared. I did some buggies and carts and balls down an incline, and you saw that with acceleration, the distance got farther and farther apart with each succeeding second? Well, that distance Galileo measured. There's an experiment. I think it's great that for many, 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 many years, people theorized about the motion of objects. And it really only took one guy, one person, to do an experiment and see, oh, no, this is how it works. So kudos for experiments and demos. But what he noticed was that the distance that something went each succeeding second was proportional to time, but not directly. I mean, it wasn't the same. You know, you add another second, you go the same amount of distance. You add another second, you go the same amount of distance. No, each second it got bigger and bigger. He measured it and plotted it out in a graph and realized it was proportional to time squared. And then he with the slope of the graph and things, he found out that it's exactly equal to this constant times t squared. This constant just happens to be 1/2 the acceleration due to gravity, and that's how we got this equation. And it works. I love this, though, because an example, I finally went to the San Francisco, the Golden Gate Bridge, and we had to walk out on it. And my sister-in-law was disobeying the signs, but I have a feeling a lot of people do. And she was spitting her gum over the edge. You know, they don't want you to throw things off. She was tired of her gum, and she littered. But she didn't tell me, because I knew this experiment. So, of course, we did it again. I figured, well, that's one. Well, I had her spit instead of get out another piece of gum. But my point is, you can tell how high up you are just by doing a simple experiment. Time how long it takes for it to go off and hit the ground. So I said, all right, you ready? Go. 1001, 1002, 1003, 1004. And it hit the ground. How high up is she? Calculate it. I'm serious. Okay, we got, if you take gravity as 10, then 1/2 of 10 is 5. 4 seconds later, 4 squared is 16. 16 times 5? 80. And 80 what? 80 meters. Yeah. Now, I grew up as a kid learning that the acceleration due to gravity it's 32 feet per second squared. It's the same value, but I had that in my head. And be honest. Well, actually, you guys are better than I am, I'm sure, because with each generation it gets better. But who can envision how far 80 meters is? Raise your hand. Do you have a sense of 80 meters? That's what I thought. Do you have a sense about 80 feet? More of you are admitting it anyway. Well, I did too. So, a meter is 3.3 or 3.28 feet, so you can convert. We'll just round to 3, 80 times 3, 240-ish feet. But let's see. If this was 32, feet per second squared for 4 seconds, 16. So we get 16 times 16, which I don't remember. If somebody's calculating it before me, shout it out. 36, 96, 16, 52. 256 feet. That was about what we approximated the other way. And lo and behold, I looked up, and that's pretty darn close, especially for me, just 1001, 1002. It's pretty cool. It works. You want to know how deep a well is? Take a pebble, drop it. 1001, 1002, 1000, splash. You know how deep it is. I think that's cool. Because Galileo figured out this proportion. Times squared. So when you drop something, it looks a lot like the carts and the balls that were accelerating. At the beginning, in the first second, it only falls, yay far. But during the second, it falls even farther. And the third second, even farther. Because it's going faster and faster and faster. Does that make sense? So before I leave that, I want to make a chart. It's in your textbook, but I want to show you something. Show it to you. Okay, I'll wait for you to catch up if you're writing it down. But let's see what these numbers are, what these values are, and make sure you really get free fall. If so, you'll be smarter than 80% of the general populace, because they deal with it, they experience it, but they don't really understand what's going on. And this works for all motion in any direction, but I want to do it with free fall, things dropping. So at time 0, we'll say it has fallen, it hasn't fallen at all, so it's 0. And what's its velocity initially? 0. See? So far, so good. All right. After 1 second, how fast is it going? Got a 9.8 and a 5. Somebody break the tie. I'm hearing more 9.8s. After 1 second, how fast is it going? It's accelerating at what rate? Yeah, 9.8. And to make our table math easier, I'm going to approximate it this time as 10. That way it doesn't get funky. So after 1 second, it goes from 0 to 10 meters per second. Now, think of just that first second as a trip. It started out at 0 meters per second. It's now going 10 meters per second. How fast was it going in between? It was accelerating. So what was its velocity between 0 and 1 second? You said 5. Would that be an instantaneous velocity or an average velocity? Average, right. If it starts at 0 and ends up at 10, the average velocity is 5. In other words, if it was going 5 meters per second the whole time, it would take a second to cover that same amount of distance. However, in reality, it was going less than 5 at one point, went through 5, went even faster, and got up to 10. So it was changing between 0 and 10 the whole time. But the average velocity is 5 meters per second. Good. So if the average velocity is 5 meters per second during that first second, how far did it go in 1 second? 5 meters. Yeah. Do you see that? Now, I'm reasoning this conceptually because that's what I like. You can plug these in. You want distance? You do this equation. You want velocity? Use this equation. And you can get it all mathematically without having to think. But I want you to think. So how fast is it going after 2 seconds? 20, because it gains another 10 meters per second. And next? You got it. So after 5 seconds, it'll be, you know how fast it's going to be going. The distance is a little harder to reason out in our head like that one. So I'll just spare you. But you can see that it increases each time more and more by a larger amount. See, during this second, it fell a lot farther than the first second. This should be 4? 40? 2 squared is 4. 4 times 10 is 40. You just forgot this part. Are you asking about this one? Yeah. Let's do it. Correct? Whoop. Whoop. There. That's 1/2 times 10, whoop, times 4, which is 20. Aha. Well, that's a good point. He mixed velocity with acceleration. Don't. They're not the same thing. And I can't emphasize that enough. People realize that, yeah, I got it, Adam, duh. But when you're trying to think these things through or do problems, people seem to still get confused, and that's often where the error is. They got velocity confused with acceleration. They're different things. So remember that. So I find it curious, though, if you plot these, let's just do it. And we don't have to be precise, but distance versus time. With each successive time, you know, it might start here and it might go to there. But the next second, it covers more distance, so it goes even higher, and so on. And so it's curved. Yes? A little louder, please. Okay. So he's asking if you could get rid of air resistance and let the thing fall forever. Yeah, as long as it's still being accelerated, meaning a force is acting on it, then yes. If there's nothing to slow it down or counter that motion, in other words, that's the only force acting on it, gravity, yes, it would go faster and faster and faster forever. Not in that case you described. We see an asymptote because air resistance. The faster you go, the more the air resistance, and that slows you down. And at some point, you reach what's called terminal velocity, in which case means terminal velocity, an high-end velocity. That means your velocity is no longer changing. So are you accelerating? No. What's the net force on you at terminal velocity? 0. You still have 2 forces acting on you, gravity and air resistance, but they're balanced. So that's why we normally don't see it. Another problem with that, though, is falling forever. In this case with gravity, what's causing it? 2 bodies. They have masses and they attract each other. So at some point, this one's going to run into that one, and that'll stop it. But ideally, if it could fall forever with no resistance, yeah, it just keeps going faster and faster and faster. In real life, we don't see that because at some point, other forces creep in to keep us from going on forever and ever. We can see that with our car. You can hit the gas pedal, and you accelerate, and you're having a good old time, but at some point, you just don't go any faster, do you? The engine can only work so hard, and there's air resistance. So eventually, you reach some terminal velocity, sideways, if you will. This one, if you plot it times t squared, in other words, instead of plotting it 0, 1, 2, 3, you plot it at 0, 1, 4, 9, 16, then it's linear. It's a straight, direct relationship. And that's what this equation tells us, shows us. That's how they got it. I wanted to show you this one too. relative velocity. We talked about relative motion at the beginning of this chapter. If this car is going at a fixed speed, let's say for argument, I don't know, 2 meters per second is its velocity. What happens if I move this board 2 meters per second this way while the car is on it going that way at 2 meters per second? So yeah, I'm going to move this at 2 meters per second, try, that way. And this is going to go at a constant 2 meters per second that way. Wish me luck. Observations. Oh. Relative, it looked like the car slowed down or lost speed. Relative to what? To the board? Do you guys agree or disagree? Did it look like this slowed down relative to the board? Relative to the table and me in the room, it did. I agree with that. Let's do it one more time. Let's put the cards here, and I'll start moving this when it gets there. Try. So its speed relative to the deck of cards was 0. However, what was its speed relative to the board? It's 2 now. When I'm moving the board at 2 also, the relative speed between the two is 4. Can you see that? So another example of, because we have multiple things going on at once. There's an example in your book of like a mosquito flying in a wind. Airplanes have to worry about this. If you're flying with the wind or against the wind, your speed relative to the ground is different. So is the air resistance. Now what if I make it 2 meters per second this way and move the board at 2 meters per second? Now what do you observe? Yeah, it's going faster relative to the table. What would its velocity be between this and the table? 4, because it's going 2 on the board by itself, but the board itself is going at 2. So relative to the table, this is going 4. Do you see that? And one more time. I lied. I thought of something else. Watch, once I start moving the board, this guy's motion relative to the board. Note where he's at on the board. I'll try in the middle, when he gets to the middle, moving the board. Watch him relative to the board. What's his speed relative to the board? 2. He's still on the board moving at 2. But the board's going along. So that might seem weird, but you're on a train moving at 2 meters per second, and you walk up and down the aisle at 2 meters per second. If the train stopped or moving, you're still moving the same speed relative to the train. Does that make sense? But relative to the ground, somebody observing outside the window, standing on the ground, you look like you're going 4 meters per second in the direction of the train, relative to the ground. And when you walk the other way, it looks like you're fighting, our first example, and it would look like relative to the ground you're not moving at all. That should help you reason some things out. All right. Yes, Brian. Oh, yeah, I love those things. Good example. The little flat escalator thingies, movable walkways at the airport, those are great. Have fun with it next time you're, I usually wait a bit so there's a nice opening so I don't plow over all the busy people. But it's the same thing. Relative to the conveyor belt, it feels like you're walking normal. But you can see outside of your eye that you're cruising relative to the floor that's not moving, or the wall. Yeah, the walls, that works too. Same idea. Then you can go the other direction, and if you walk at the same speed, it's moving the other way. Looks like you're not making any progress at all. That's always fun. Thanks, Brian. All right, get your clickers and devices out. We'll do some questions. See if you're getting this. Yes? Relative to the ground that's not moving.
In Newtonian physics, that's zero, right? But in real life, don't you have to add in some sort of adjustment? I thought, didn't Einstein decide that there was some sort of...
Oh, do you need some adjustment? I think what you're getting at is when you start, the velocities approach the speed of light, and you're going a lot faster than normal speeds. Technically, it's not because of Einstein's theory of relativity. It becomes more apparent when you're going at higher speeds. It's still there at low speeds, slow speeds, but it's usually negligible. And what he's getting at is you have to make an adjustment due to relativity because it starts warping space-time, and I'm happy to discuss it later. Hold on. Just a sec before I leave that topic. GPS and your phones using the satellites in space, if they did not take into account this adjustment because they're going fast relative to, they wouldn't work. They'd be useless because the times would be off. So if satellites did not account for theory of relativity, the slight adjustment we're not going to discuss, they wouldn't work at all. Correct. Gravity does decrease with distance. That's correct. The acceleration due to gravity is less the farther away you get from Earth. So a satellite up in space, it might be, well, it's less than 9.8. What degree is that relevant, the 9.8? They have to take that into account as well, definitely, because the acceleration is different. So all those values would be different for velocity and times. And if they don't use the right value, they'll get the wrong answers, yes. Good observation. All righty. So that, you guys need to see the session number first. There it is. Why is this not playing with PowerPoint? There we go. Bottom right, clicker on channel 44. Your mobile device, you can log in with that session ID number. Yes?
Is it possible to set up your last name as the session ID? Because I have other professors that have set up their last name as the session ID.
Oh. I was told to log into ResponseWare like you do, and it gives me a session ID number. That's what the software people told me. If it's possible to make it permanent, I will look into it. I don't know yet, but I'll check. Okay. Polling is now open. Let's see what you think. And as I learn how many of you have your clickers, I can start counting down. It's looking close. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. The large majority said B. You're correct. Any questions? Those that missed it. Distance divided by time gives that speed. Okay? I want to ask this one. Go. Polling is now open. $20 seconds. 10 seconds. 5. All right, the large majority, 74%, chose D. You're correct. Questions? Concerns?
Because I answered C, because I was assuming in one direction, and I thought about it, yeah, D is right.
Yeah, that's usually where people miss this, is they assume one direction, you get one answer. You assume the other direction, you get another answer. But it didn't give you the direction, so D is the correct answer. Polling open. $20 seconds. 10 seconds. 5. All right, less of a majority chose C, 62%. The next favorite was B. Let's look. So somebody that guessed B, why'd you say that? Be brave. It's okay. Picks up 4 meters per second. Its acceleration is. So you took as an average. Okay. Okay. Anybody want to add to that? Or a different reason you chose B? Okay, how about C? Somebody defend yourself on C. Velocity over time? You're just counting the seconds. You want to add to that? My thought, oh yes.
It's picking up 4 meters every time in each second, so its velocity would be that every second squared. So
Yeah, if it's let me get it right. Picks up, is the word, increases 4 meters per second every second, then it's 4 meters per second. 4 meters per second squared is the acceleration. And it's not an average because it does it every second. If that would have just been like one case, one of the second intervals, maybe. I think I had another one I wanted to do. Yeah, let's do this one. Polling open, 30 seconds. See if you remember. Ten seconds. 5. 74% chose D. Very good. You have to remember that acceleration is a change in velocity over time. And velocity is a vector. So it can speed up, slow down, or change direction. Even if it's staying at constant speed and turning, it's accelerating. No. No. That one. Go. Ten seconds. 5. Most chose A. Questions? Why did someone choose not 0? I'm curious. Because that could be the right answer. Because you chose non-zero because gravity's still acting on it? Yeah. Okay. Gravity is still acting on it.
Because it's not in equilibrium.
At the top? Yeah. And she says it's not in equilibrium at the top. Anybody want to add to that? Yes?
So even though it's not equilibrium, when you throw it up, it has to go to 0 at some point and then start to come back down. So
Yes. The correct answer is A, 0. At the top, it's not moving. Right? There. Right? There. At the top, yeah, it's not moving right at the top. So its velocity is 0. What's its acceleration? At 10 meters per second squared down. What's its acceleration on the way up? 10. How about on the way down? 10. Gravity's always acting. So you were right about that. So its acceleration is not 0 at the top, but its velocity is. Yes?
So the only time it's not 0 is if it's not thrown like exactly vertically?
So like this? Technically, yeah, it's not 0. You help me just say why if you do this. Right at the top, at the peak, which way is it moving? Yeah, at the top, vertically, its velocity would be 0 at the top. But if you throw it like that, horizontally, it's still moving at the top. So when you're doing that, we're going to study that in Chapter 10, Projectile Motion. So when I throw it up, it has a horizontal velocity and a vertical. But the vertical gets less, goes to 0, then it ends up going back down. But it's two different directions we're dealing with in two-dimensional motion. Other questions? Okay. Good job. Eight minutes. I want to do, which one of these do I not want to set up Friday? This one. This ball is heavy, and I'm hanging it from a not so strong string. If I pull on it downward, it'll put tension in the strings, both strings. Right now, the string can support the weight of the ball. Its mass is being accelerated down, so mg is its weight. And in equilibrium, the tension balances that. And I want to state, when the ball's at the top of its thrown, at the top we would say it's in equilibrium. So this is in equilibrium. But I'm going to push down and add on top of its weight. Which string will break? What do you think? Here goes. I'm pushing, I'm pushing, I'm pushing. The top one broke. So this I do to emphasize that's overcoming its weight, because I was adding to the weight that top string was feeling. Let me hook it up again. Not only did the top string have to support the ball's weight, but the additional force I added. So it had its weight and my force. And the total down was trying to balance the total up. And it wasn't enough. The string couldn't handle it. That's to emphasize weight. Now, I would like to emphasize mass. I think I heard it over here. It depends. This time I'm going to push down again, but I'm going to do it quickly. Ready? Watch. Now the bottom string broke. That is to emphasize this has mass, so it also has inertia. And it wanted to resist that change in motion. And so mass can be accelerated downward and give us weight, but it can also resist motion, change in motion, because of its inertia. There's a big difference between mass and weight. And that's another one people get confused. And we're going to finish this next lecture. This will allow us to do Newton's second law. I'm going to tell you that acceleration is proportional to force. The harder you push on something, or pull, the more it's going to accelerate. I hope that makes sense to you. Yes? No? Maybe so? Somebody react. Does that make sense? Even before this class, probably? If you push on something harder, it's going to move faster, have a greater change in motion. But how do we say it's proportional to mass? Do we write an m? If we increase the mass, does it accelerate more? No, it's less. So we say acceleration is proportional to the inverse of mass. It's an inverse relationship. That just means, look at it mathematically. If m gets bigger, this gets smaller. There's more resistance to change. Can you see the connection? Newton just put it together. Bigger force, that'll make A bigger. But increase the mass, and that'll make A smaller. And that's Newton's second law. That equation, that relationship, tells us what we've been studying all along. You've already been using it, but I hope you see the connection a little better now, so it's your friend instead of just a scary equation. Any last-minute questions? All right. Just a friendly looking forward. So Friday, I'll finish chapter 4, yes, on Newton's second law. Monday is a holiday. Don't come here. Wednesday, we'll do chapter 5. All right. See ya.